the recording, and we'll start with some general announcements. Okay, so it looks like the recording started. So I wanted to start today with a few just kind of general announcements. First, I'm just finishing up the first set of lab reports. My goal is to get those posted to Canvas later this evening. That way you guys have some feedback before the second lab is due. Just a reminder that the second lab is due in lab this week, or the end of the day during the day that you had lab, so either Tuesday or Wednesday. So just a reminder to continue working on the CFR Engine lab reports. A side note, we will not be meeting in person this week, so you don't have to come into the lab, but I will be available for on Teams for any sort of questions that you might have during the individual lab periods. So if you do want to essentially use that time to finish up the lab reports in your groups, ask some last minute questions, I will be available, but I will not be in the lab in person. Everything will be done by Teams this week. So just a heads up about lab this week. Otherwise, I wanted to remind everyone that the psychometrics first reading quiz is due today. So if you haven't taken time on Canvas to go ahead and do that, it's a reminder to try and get that done before the end of the day. Essentially, it'll be a few questions on kind of the basics of psychometrics. And I think the first homework then is due also tomorrow, if I remember correctly, for psychometrics. So basically dealing with some of our fundamental terms. Otherwise, we'll be continuing psychometrics this week. We'll be working an example today. We'll be pushing into what the psychometric chart is, and then we'll get into air conditioning processes by the end of the week. So that's the current setup. The next homework set has also been posted, so homework number 5, dealing with the kind of air conditioning processes. We'll be talking about that a little bit later this week. So those are the general reminders. Main thing is no in-person lab this week. Use that time to work with your groups, finish up the CFR Engine report. Okay. Otherwise, the main thing I wanted to start with today is the example problem that we were just about to get to last week, and that is example 12.7 here. This is dealing with a 1 pound sample of moist air. The air is initially at 70 degrees Fahrenheit at a pressure of 14.7 pounds per inch squared, PSI, and it has a 70% relative humidity. It's going to be cooled to 40 degrees Fahrenheit while keeping the pressure constant. So it's going to be an isobaric process. We have to determine the initial humidity ratio, the dew point temperature, and the amount of water vapor that is going to condense in pounds. So what we want to go ahead and start with is just writing down all of our knowns. And in terms of what we know for this process, well, we are given the total mass. This is just going to equal 1 pound. We are given initially a dry bulb temperature, so this is T1. We'll call this T dry bulb 1. And this was going to be 70 degrees Fahrenheit. So remember, the dry bulb temperature is the same as the actual temperature that we measure. Additionally, we were told the total pressure. The total pressure at the initial state is going to be 14.7 psi. And we'll note that this is an actual pressure, not a gauge pressure. And then we also have one last thing, and that is we have a relative humidity. At state 1, this was equal to 70% or 0.7. And those were our initial conditions. Now we're going to be cooling this down to the final state. So this would be the final temperature, T2. Note this is the dry bulb temperature at state 2. And this is going to equal 40 degrees Fahrenheit. So we have our final state, and we'll note that this is done in an isobaric fashion, so P2 is equal to P1. Now in terms of kind of drawing this system out, let's go ahead and try and put a visual to this. And basically what we're going to do is we're going to have a piston cylinder style setup. And so what this means is as we're going to be changing the temperature to maintain a constant pressure, we're going to have basically the piston be able to move, and that way the pressure in our system remains constant. And so this is basically the setup that we have. Now we'll go ahead and note that we're going to be dealing with moist air. And so the moist air represents the air plus the water vapor inside of our system. And we'll note that we're going to be cooling it down. So we'll just go ahead and note that we had some sort of heat transfer out that's going to cause some of this water to condense. And so we want to look at how do we go about mathematically modeling this, and what are the things that we need to find, what are the things that we need to assume. And so in terms of our find statement, what we're looking to do is first go ahead and use what we know to calculate the humidity ratio at state 1, also called the specific humidity. We're also going to then move on to the second part, which is to calculate the dew point temperature at state 1. And then for part C, we are going to calculate the mass of the water that condenses, the amount of liquid water that we have inside this cylinder after we change the temperature. And so that's going to represent what we're going to be looking for. Now, in terms of getting to the final point, we're going to have to make a few assumptions. So let's go ahead and write down everything that we want to assume in terms of our analysis. We're going to note that this is going to be a closed system. We're going to note that we're going to be dealing with a stationary system. We're going to also assume that we have ideal gas and an ideal mixture. So those were kind of our base assumptions leading into kind of the psychometric analysis that we needed to do. And so those are going to be the main things that we're going to have to assume. And so once we've got that down, we can go ahead and push forward into the actual analysis for this. Now, in terms of the analysis, we're going to start by looking for our first deliverable. That is going to be the humidity ratio here at state 1. And if we recall from the base definitions, we said, well, the humidity ratio, that would be the mass of the water vapor at state 1 divided by the mass of the dry air at the first point. Now, we don't know either of those, but what we did show is if we know that this is an ideal gas, we can relate these to the partial pressures. And we could do that, and when we ended up with was the kind of a constant out front here, that was 0.622, which was the ratio of the molecular weights. We then had our partial pressures. We had P of the vapor at state 1 over the total pressure at state 1 minus the partial pressure of the vapor at state 1. And so what this was the partial pressure of the vapor divided by the partial pressure of the air. We said we could relate the air, because we're going to assume that there's only two parts, to the total pressure and then the partial pressure of the vapor. And so we'll note at this point we were given the initial pressure, that was 14.7 psi, and we only other variable here was the partial pressure of our water vapor. And so we just need to now determine what is the partial pressure of the water vapor to make this calculation. Now, if we think back to other things that we know, because we're going to have to use another definition. Well, if we just go up to what we were given, and I'm just going to scroll up here for a second. Well, we were given, we have a total mass, we have temperature, pressure. And we were also given this last value right here. This was our relative humidity. And so we said, well, let's go ahead and see if we can do something with the relative humidity. Now, the relative humidity at state 1, by definition, well, we said that was going to be the mass of the water vapor divided by the mass at the saturation condition of the water vapor. And when we did the ideal gas analysis on this, what we ended up finding was this is equal to the partial pressure of the water vapor at state 1 over the saturation condition and the saturation pressure at state 1 for the same gas. So again, these are at the same temperature. This is going to be at T dry bulb state 1 for both of these lookups. And so at this point we said, well, we were given this value that was 0.7. So if we rearrange this, we can now find the vapor pressure of the partial pressure of the vapor. That's going to be a function of the relative humidity at state 1 times P sub G state 1. And so we just now need to look up what is P sub G at state 1. Now remember, P sub G was the saturation pressure at the given temperature. And so if we go over here and we pull up Appendix 2, well, we just need to know the temperature. That was 70 degrees Fahrenheit. And so we're just going to look right here in the table. We found P saturation at that point, and that is 0.36334 psi. And so that's the value that we're going to use here. So we'll use P sub G1. We looked it up at the given temperature, and again, that was 0.36334 psi actual. And so we have our first lookup value. Once we've looked up this value, again, we know the relative humidity, so we multiply that by 0.75, and we can get the partial pressure of the water vapor. This is going to be 0.25434 psi, and we'll note that that's the actual pressure. And so we see that the partial pressure of our water vapor is very, very low in terms of the total pressure. So it's only a small fraction. Because it's at a low temperature, we had to look up the saturation condition, and that is what the value is. So again, the partial pressure of the water vapor will always be very small, which again tells us that water is only a small component of the moist air. Okay, so now that we have the partial pressure of the water vapor, we said we now have a total pressure, we have a partial pressure, we can go ahead and complete this calculation. And so we can complete the humidity ratio at state 1. This is going to equal 0.01095. And the units on this is going to be a pound of vapor divided by a pound of dry air. And so there we go. We have our first calculation for our psychometric system. That is the humidity ratio at state 1. And so all we did here is we combined our base definitions. We used a table lookup, and we were able to find that initial point. Okay, so now we can go ahead and move on to part B. And in part B, we were asked to figure out what is the dew point temperature. Now, if we recall the dew point temperature, our base definition for this is going to be T dew point. This is equal, this is equal, dew point temperature, this is just equal to the saturation temperature at the given partial pressure of the vapor. And so we have to go ahead and do this lookup. Now, before we go too far, I do want to draw a TS diagram to kind of give us some visuals on this system, just so we are keeping track of what we're doing and where we are going in the table. So this is S, this is going to be our T-axis. We'll go ahead and draw in our vapor dome here. Try and draw that mostly to scale here. And so we're starting somewhere out here. This is our initial point. And we're going to have to figure out some temperatures. And so we'll do temperatures here in red. So if we drew a dashed line over to the left-hand side, this would equal the dry bulb temperature at state 1. And so again, we'll note that this is state 1. We'll label it here once we get all of the lines in here. And so again, that is the first temperature that we had. Let's go ahead and get some pressure lines in here. We'll do those in green. So we have the partial pressure of our vapor. Let's do a little shallower here. And so this is going to be the partial pressure P vapor 1. And again, this would go down over here. And so that would be the vapor pressure. We already looked up P sub G1. So let's note that P sub G1 will be calculated right here. So this is now P sub G1. And at the temperature of 1, and so we looked up that pressure right there. And so what we want to do is we want to find the dew point temperature at state 1. And so if we go back here, we said the dew point is the saturation temperature for the given partial pressure. So what we do is we follow our line of constant pressure down here. We said, well, where this phase change would happen, we would draw a line like this. And this is the dew point temperature at point number 1. And so that would be the temperature, if we just drop the temperature, where condensation begins. And so we'll just go ahead and look this up. So we want to find T saturation for the given partial pressure. Given partial pressure was 0.254. Now, what I want to point out here is if we go to the appendix, the normal thing that we'd want to do is we said, well, we know a pressure, so let's go to the pressure table for our lookups. What we'll note is the lowest pressure is pretty high, so 1 psi. We're at 0.254 psi. So we can't get to the data that we need using the pressure table because we don't have a point that's lower than 1. We can't do any linear interpolation. So what we have to do for almost all of our psychrometric calculations is we go to the temperature table. Even though we know pressure, we're going to use the temperature data for our linear interpolation. And so if we looked at this, we had our temperature being, I should say our pressure was 0.254. And so if we look, we said 0.256. We have a value 0.214. So it's going to be somewhere between 50 and 60 degrees Fahrenheit. And so we'll have to do a little linear interpolation, but 0.256 is pretty close to 0.254. And so we expect it to be pretty close to 60 degrees Fahrenheit. And so I'm going to save us some linear interpolation here. And what we're going to find is if we go to the table, the dew point temperature for state number 1, this is going to equal 59.8 degrees Fahrenheit. And so this value was determined just from using the partial pressures and going to the table for our lookup. And so that's it. That's all we have to do for the dew point temperature. We would basically just say, well, we're cooling it down to the saturation condition using the partial pressure of the vapor, and we can now calculate that temperature from the lookup tables. And so basically what we've done is we've gone 2 different points in the table. First, we looked up the partial pressure at the given temperature for the saturation. And so we looked up P sub G. Again, that was using the temperature that's known. Then we can also repeat the process using the partial pressure that's known, and that would be our dew point temperature. So again, keeping track of what goes where in terms of the lookups is important. And so what we can see here is that, well, if we want to move on to kind of part C here, part C was asking us how much water was going to essentially condense in this process. And we said, well, instinctively, what we can say is the dew point is the temperature where we will have condensation begin. Our final state is at 40 degrees Fahrenheit. So 40 is less than, well, we'll just say 60 for rounding purposes. We are going to have condensation occur because the temperature is going to go below this point. Now, there's a few different ways that we could calculate this. And so the first way is just to do this calculation. And we said, well, we know that our state 2, so T2, is going to be less than T dew point 1, so we could have condensation. Now, this is the first way. This is what we did already. This is what the problem was kind of leading us to do. But there's another way that we could check this if we weren't able to kind of make that calculation right off the bat, or we didn't want to do maybe a table lookup. So I'm going to do is I'm going to say, well, that's kind of our first example showing that we know condensation is going to occur. The other thing that we could note, if again we weren't sure of what was going on, so we could figure out what's going to be held constant in this process, and we could make a comparison. And so in this process, we're cooling it down. And so if we didn't have condensation occur, what would happen? What would happen if we maybe had a temperature that was higher than our dew point? If we thought about it, in this case, what would happen is no phase change would occur. So we could say, well, that means our humidity ratio here would equal a constant, right? And so if we could say our humidity ratio is a constant, maybe we could use this to kind of check the far point. Now, again, I want to point out it's not constant all the way through our process. It would only be constant outside of the two-phase region. So when it is a vapor, we could say that it's going to remain constant. Now, the reason I want to show you this technique is because this is the technique you're going to need on, I think it's your second actual homework problem. So that's the one where you're going to be looking at some partial pressures, and you're going to have to try and figure out how much of a change happened in the system. And so again, this is the sole reason that I wanted to discuss this. And so if we can assume right now that W is going to equal a constant, well, let's just go ahead and see what happens when we say W1, humidity ratio of 1, has to now equal the humidity ratio of 2. And again, all that we're saying here is that we have the mass of the vapor over the mass of the dry air equaling a constant. And so this is what we mean by we have a closed system. We can't have anything change that. And so we just want to see what happens if we make that assumption. And so what we can say is we calculated W1 up here. And so we can go ahead and set this equal to W2, so 0.622 partial pressure of vapor 2 divided by P2 minus partial pressure of vapor 2. You can now say this would be 0.622 partial pressure of the vapor at 1 divided by P1 minus P vapor 1. And so in this case, we know P2 and P1 are the same. And so what that would mean is we'd have to have P vapor 2 equaling P vapor 1. And so in this case, what we could do is we said, well, let's figure out what the relative humidity at state 2 would be. So we can say, well, what would this V2 be? We said, well, according to definition, P vapor 2 divided by the P sub G at the given temperature. Call this T2. And so we just have to look up P sub G at vapor state number 2. And so we can say PG2. If we go to the table lookups for this, again, this is the saturation at 40 degrees Fahrenheit. What we'll find is this is equal to 0.12172 PSI actual. Now, why did we do this? Well, let's compare these numbers that we have. So we have P sub G2, we have P vapor 1, so we could say now we have P vapor 2 equal P vapor 1, to be 0.25434 PSI A. And if we compare these two and calculate our humidity, relative humidity here, we can see that the vapor pressure at 2 will exceed the saturation pressure, which would mean that the point would not work in the superheated region. And so what that means is our relative humidity here would be greater than 100%. And so in this case, we could see, okay, that makes sense. This would have condensation occur. And so again, this is just a separate method for calculating that same information that we already know, but it's going to be somewhat similar to how you're going to approach the homework problem. So I wanted to kind of show this. And again, that's for this process. If we wanted just again to check where that point would be, we could assume the humidity ratio was constant until we hit the saturation point. In this case, because we hit the saturation point, we'd be inside the vapor dome. Well, in that case, we can't assume the humidity ratio is constant for the entire process. It's only constant for this portion of the process. So now that we've seen two different ways of proving that we're going to have condensation, let's figure out what actually happens in this case. And so in our actual process, we are going to cool it down. And so because the pressure is constant, because we aren't changing phase during this process, we are going to move along the partial pressure vapor line right here for the water. It's going to reach this saturation condition. With this saturation condition, this means we have a relative humidity of 100%. And at this up until this point, the humidity ratio remained constant. Now, once we hit the saturation condition or we reach the dew point temperature for our system, that's when we start to have condensation. So as we continue to cool this system, we will have some water come out of the air. Now, the air will always remain at a saturated condition from this point forward. And so the water vapor that remains in the air will move along the saturated vapor line. And so when we get to the final state, it will be right here at the saturation condition. And so if this was state 1, this will be state 2. This is our final state. And what we can note here is this would be the final temperature. So it would be our dry bulb temperature at 2. And we'll note again, the final state is going to have a relative humidity of 100% because it's going to be saturated. As we continue cooling it down, water will keep coming out of the solution, but the amount of water vapor is always going to be the maximum that we could have. And so we will move down to state 2, but we'll also have some water that will condense out. And so this would be the amount of water that condenses. We can assume that is a saturated liquid at this point. And so make a note here that this is, well, we could note that this is going to be P sub vapor 2. And so we could have a line that goes up like this. And so what we're going to be most concerned with is the partial pressure of the vapor 2 now that we had some water come out of solution. And so what we want to do now is turn that into how much of the water came out in terms of a mass. And so to do that, we're going to move on here to part C. Part C, we're looking for the mass of the liquid water. Now, to get the mass of the liquid water, we are going to have to use conservation of mass. So that's going to be our key thing here. And we're going to do it on a species analysis. So for conservation of mass, noting that it is a closed system, we'll start with air. The change in the mass of the air for the system, by definition of a closed system, we are having a control mass. We're just tracking the same amount. So we can have no change in mass of the air. What this means is the mass of the dry air at state 1 has to equal the mass of the dry air at state 2. And so we can generally say that this is just the mass of the dry air. And so that's nice, but why does that help us? Well, let's go ahead and take a look at the water side. And so the water side includes both the liquid water and the water vapor. And so noting that we have a closed system, so delta M of the water, we note that this has to equal 0. And we said, well, this would equal the mass of the water, and we'll call this mass final state minus the mass at the initial state. We'll just call that I. And so we have this change in mass that has to equal 0. But what we know intuitively from just what we've done before, we said, well, we know water is going to condense out of this system. And so that means our final state is going to have both some water that remains in the vapor state, so mass of the vapor. We will then also have some mass of the liquid water. We'll call that W because it'll be liquid water. And that would be the total mass at the final state. And then we have minus the mass at the initial state. And so that's just all vapor because we knew it was a vapor state, and so we have minus mass of the vapor at 1. Now what we can do is we can rearrange this, and so we can solve now for the mass of the water. Since this has to equal 0, we can now say this would equal the mass of the vapor at the initial state minus the mass of the vapor at the final state. Now this is useful, but we have to delve a little bit deeper. And so what we could say is, well, if we wanted to, one way of looking at this is we could just multiply by a constant. That'd be the mass of the dry air over the mass of the dry air. Then we'd have mass of the vapor 1 minus the mass of the vapor 2. We'll note that the mass of the air was the same for both states. So we could do this with 1, we could do it with 2. It doesn't matter because it's the same. But what we really want to do is we want to bring this per mass of dry air, we want to bring that through. And so what we could say is, well, we have a mass of dry air out front, but then we have the mass of the vapor divided by the mass of dry air. So by definition, that was our humidity ratio. And so we can substitute in now the humidity ratio at state 1 minus now the humidity ratio at state 2. And so now we just need to know the mass of the dry air and the two humidity ratios. And so what we want to do is go ahead and calculate what is the humidity ratio now at state 2. And so we can go ahead and use our definition, 0.622 times the partial pressure of the vapor at state 2 over the pressure at state 2 minus the partial pressure of the vapor at state 2. And so the other thing that we note is for the final temperature, well, we've had water that condensed out, and we said because water was condensing out, that means we had to be at the saturated state. So we have one other piece of information at this point, and that is the relative humidity at state 2. It's going to equal 100%. And so if it's 100%, we can go ahead and say, well, it means P vapor 2 has to equal P sub G2. And we'll note that P sub G2, we looked it up right up here. That would equal 0.12172 PSI actual. And so now at this point, we have the partial pressure at 2. We can get the partial pressure here. We can substitute that into our humidity ratio at 2. We find the humidity ratio at state 2. This is going to equal 0.00519 units, or a pound of vapor per pound of dry air. And so that gives us the humidity ratio at point number 2. So we'll note that we need the mass of the water. This will equal the mass of dry air, humidity ratio of 1 minus the humidity ratio of 2. And so we now have humidity ratio of 1. That was our first calculation. We now have the humidity ratio of state 2. But we're still missing one thing, and that would be the mass of the dry air. And so we can note that, yes, we have one of the pieces, but we're still missing the mass of dry air. So let's go ahead and see if we can figure that out. And so if we think back to what we were given, well, the first thing that we were given is that the total mass of our system that we had for the moist air, this was equal to 1 pound. Now, we can go ahead and say, well, the total mass of the system, this would equal the mass of the dry air plus the mass of the water vapor. And we'll do this at state 1 because we had all of the water in solution at state 1. And so we have this set up. Now we can go ahead and say, well, we used this trick where we multiplied by the mass of the dry air. And so we could do that down here to convert the mass of the water vapor into the mass of the dry air times the humidity ratio. And so what we end up with is we have the mass of the dry air plus the mass of the dry air times the humidity ratio at state 1. And so again, that's just recalling that the mass of the vapor is equal to the mass of dry air times the humidity ratio of 1, because all of the water vapor was in the air at that point. And so that's the substitution we've made. And so we can go ahead and say, well, that means the total mass, this would equal the mass of the dry air 1 plus the humidity ratio at state 1. And so we could go ahead and rewrite this into the mass of the dry air, be the total mass divided by 1 plus the humidity ratio at state 1. And what we find is the mass of the dry air is equal to 0.98917 pound of dry air. Now, if we want to go ahead and just do the final calculation, we could say, well, the mass of the water vapor at state 1 is equal to 0.01083 pounds of vapor. And so what we can see by this is we said, well, mass of the water vapor, it's pretty small. Most of the air, or most of this moist air is just going to be dry air with a little bit of water vapor, which now we can say makes sense. But why did we do all of this work? Well, what we did is we wanted to calculate the mass of the water that's going to condense. So we can now take the mass of the dry air, we have our two humidity ratios, and we can go ahead and find the mass of the water that condenses. This is going to equal 0.0057. Units on this are going to be a pound of water. We'll just go ahead and do that. And so we can see that the amount of water that we have condensed is very small, but there is a large amount of energy that is associated with this phase change, and so it's important that we consider that. And so, again, this was just a practice using all of our definitions, applying some mass balances to try and work through all of the calculations that we need for this system. Okay, and so the important thing here to remember is making sure that you get all of the lookups correct, making sure, again, that you can kind of visualize the process on any sort of phase diagram. Here we used a TS diagram. We can see what our partial pressures were and where we had to look things up in the table and kind of why we did those lookups for this given problem. Okay, so that is going to be the end of this example problem. So if you have any questions about this, please let me know. Otherwise, at this point, what I want to do is I want to go ahead and switch gears and push into kind of the new topic for this week, and that is going to be the psychometric chart. And so the psychometric chart is going to be the kind of new piece that we're going to be talking about this week. And so this is going to be very important for HVAC kind of applications. We're going to be using this quite often in terms of our discussions, trying to help with our analysis. And so that's why we want to spend a little bit of time working with this. Now I'm going to see if I can fix the screen here. So give me 1 second. See if I can get this to show up. Okay, well, looks like we'll just have to go with this. As it is. Screen's a little messed up right now. Okay, so the psychometric chart is what we want to use to help bring all of these terms together, help us kind of visualize what's going on in terms of air conditioning processes. And so before we get into what is the psychometric chart, we want to talk about what were the key terms that we need to know for any sort of process. Now, in terms of these process terms, the first is going to be that we need to have the dry bulb temperature. If you remember the dry bulb temperature, it's our standard temperature that will be measured by any thermometer. This is going to be one of the key measurements that we will make. And so we're going to want to include this on the chart. We're going to want to be able to figure out what the wet bulb temperature is. This is important for like the adiabatic saturation temperature. This was historically used with the psychometric chart to help determine the initial state. So we're going to want to be able to figure out what the wet bulb temperature is. We're going to also want to be able to find the dew point temperature, because that's going to tell us if we drop below a certain temperature, we'll have water condense. And so we need to know that, so we're aware of where we are for phase change. We're also going to want to include our two new terms, so our humidity ratio, which tells us the amount of water vapor in the air. And we're going to need to also have our relative humidity, because this was kind of the term when we talked about kind of atmospheric science. We said that's pretty much the most common value that we have. They said that's pretty important for human comfort. Humans generally like somewhere between 30 to maybe 60% relative humidity. If we have too high, then they said it doesn't feel very comfortable. If it's too low, it feels very dry. And we said, well, somewhere between maybe like 30 to 60% is pretty good for comfort. Generally about 30 to 50% would probably be considered standard. And so we want to be able to relate all of these terms, and we want to be able to do it for most HVAC processes. And so that's the whole purpose of the psychometric chart. And so the psychometric chart brings all of these concepts together for HVAC systems, so heating, ventilation, and air conditioning systems. And so one of the things that we should note for HVAC systems is that we assume that the total pressure is essentially 1 atmosphere. And so if we're dealing with 1 atmosphere of pressure, then we can say use this chart to do all of the lookup. So it reduces the number of variables we're going to need down to essentially 2, because we're going to fix the pressure at 1 atmosphere. So if you think of atmospheric science, everything is about one atmosphere. If you change positions on the globe, so if you were in like Denver, it might be a little different, but we can use this as a pretty good approximation for most HVAC systems. And so what we wanted to do is create this visual and put all of these pieces together. Now, this is kind of a simplified view of what the psychometric chart's going to do, and we'll look at what we can find on the chart. And so what we want to be able to read is we want to be able to read our temperature. So the dry bulb temperature, that's our actual temperature. We said that is going to be one of the most common measurements we have, so that's going to be the x-axis. One of the most important outcomes that we want is our humidity ratio, which our humidity ratio is also called the specific humidity. So we're going to put that on the y-axis so we can easily look that up once we have established where we are. And so we're going to be able to look that value up. And so we wanted, again, to be able to draw a straight line, get that value with some precision. That's going to be on our y-axis. In terms of other data points that we can consider, well, we have our relative humidities. So we're going to have several lines of relative humidities. They're going to be parabolic shapes that go like this. And so again, these will be constant specific or relative humidities. And we'll note that the special case that we'll pay attention to is the saturation line, which would be the constant relative humidity of 100%. That's going to give the psychometric chart its very unique shape because nothing can exist to the left of that line. And so we're going to end up with this left hand kind of top left corner being cut off by this saturation point. So it's going to have this kind of cut off part of the chart. And so that's going to be, again, the saturation points. And so these are just going to be lines of constant relative humidity. Now, other parts that we'll be able to see on the chart is we'll have lines of constant specific volume. Now, these are going to be kind of up diagonal to the left, and we can use these, but for the most part in this class, we won't need to use this portion of the chart. If you do want to take an HVAC course, you would, of course, use these. Now, the last thing that you will note is we have 2 diagonal lines. One is going to be a wet bulb temperature equals a constant. One will be enthalpy being constant. Now, these are shown as being slightly different, which of course they are. But for most purposes, these end up being so similar that we could almost assume one is equal to the other. Now, the reason for that is if we go ahead and just consider what the adiabatic saturation condition was. Well, we had the air condition plus the amount of water that we had in the air coming in, plus then we had some water vapor, water that came into the air. So this is just rewriting what we did last week in terms of the adiabatic saturation setup. So H air plus the humidity ratio at 1, H sub G1. We'll note that this is again at state 1. This would be state. Oops, that would be state 2 over here. State 2, 2, and 2. Then we had 1 over here. Now what we can do is we're going to go ahead and combine these terms into a single enthalpy. So this will be H2. This will be H1. And so what we'll note is we get 0. This is equal to enthalpy 1 minus enthalpy 2. Plus then we have W2 minus W1 times the enthalpy of the water. And so what we're going to see And why these lines are so similar is, if we recall from the example we just worked, W2 and W1 are our specific humidity ratio, our specific humidities. Those are pretty small numbers. And if we actually go to the numbers we got before, state 1, we had W1 was equal to 0.010, or say 0.11 roughly for the first one, and the second value we had was 0.005. And so we see that we're basically looking like 3 decimal points out for those, and the change in that is going to be pretty small. And so we say that this value is pretty small, and we said, well, the enthalpy of water in terms of the liquid side, that's much lower than our vapor side, and so we can kind of say that this value is small. We'll just kind of say it's almost 0. And so what we'll see is the lines of constant wet bulb and constant enthalpy basically will be the same. And so at this point, let's go ahead and just go and see what the chart looks like. Now, this chart is the one that's in the back of the textbook, so you can use this one. This would be the one you can use for the lookups. But I also wanted to provide 2 other forms. So this is the same version of the chart, just printed in a higher resolution. So it's got much higher readings. And this is the I think this is the SI units, so SI units. And then I provided one also here. This would be the English unit version. So we can do this in both sets. These are again from the American Society of Heating, Air Conditioning, and Ventilation. So basically ASHRAE, same thing that we have here, just a higher resolution. So it's a little bit better for your lookups. And so this is what the actual psychometric chart looks like. And so we're going to need to be able to use this for some of our homework problems. And so a few things that I want to point out about the chart. So the first thing that we have over here is the left-hand side is always going to be, or the right-hand side, this is going to be the humidity ratio. And I want to point out that the humidity ratio is going to be these values right here on the inside portion of the lookup. And so again, this is the humidity ratio. And the thing to note about this version is this is going to be a gram per kilogram in terms of the units. And so it's kind of hard to see here, but we have gram per kilogram of dry air. So this is where you do have to pay very close attention to all of your lookups and all of the units on your calculations. And so that is the humidity ratio. In terms of other parameters, we see that we have these diagonal lines coming up. These are lines of constant relative humidity. And so we can see that we have these values here. And then we have the saturation line over here on the left-hand side. That is the kind of limiting case. And so that would be the 100% relative humidity. Now, in terms of the diagonal lines, you can maybe see here that you have some dashed lines here. Those would be constant wet bulb temperatures. And if we look really carefully, there's a case right here, the wet bulb temperature. Well, you can see that it's almost parallel to the solid lines. The solid lines here are the lines of constant enthalpy. And so generally speaking, we can kind of assume both of those will be the same. And so that was that argument that we were making on the previous slide. Now, in terms of being able to read the enthalpy, if we read all the way up here on the left-hand side, we have the enthalpy that we can read directly off of the chart. Now, the enthalpy that we're going to use, this will be H. This is going to equal the H of the dry air plus the plus the humidity ratio times the saturation enthalpy. And so what this ends up being is this is C sub P times the temperature plus the humidity ratio times H sub G. Now, the one thing I do want to note is everything that we've taught you before, when you're using the psychometric chart, you will use degrees Celsius for the calculation for the numbers to work out. So C sub P times T. T is not absolute, it is your relative degrees Celsius for this enthalpy calculation. And so that is the one thing I want to point out at this point. Now, how do we use this to make some measurements? Well, let's go ahead and take a look. And so let's use a temperature of about 30 degrees, and we'll come up here, we'll put a point right here, and we'll say that this is our data point. Now we're able to make a lot of measurements off of this, and so the first thing to note is if we just move straight vertical, this would give us the dry bulb temperature. So T dry bulb, this is equal to 30 degrees Celsius. So that's the first lookup value that we want. Now, in terms of other properties that we can look up, if we go ahead and just move directly to the right, we can get the humidity ratio. And so humidity ratio here, so this would be 14, 14.5, 15. So you can say, well, this is about 15.5 grams of vapor per kilogram of dry air. And so we can get that just from the lookup table. And so those are going to be the first two things. I'm just going to go ahead and try and finish this up because it shouldn't take too long to quickly get this done. And we can review this. Other parts that we can look up, well, we have a relative humidity here of 60%. This is a 50%. And so if we look at this point close enough, we could say, well, let's just assume here we can have a relative humidity. Let's just say 58%. It could be 59%. We're going to have to ballpark that using the chart, but if we're close, we'll take that. That's a value we can take a little bit of uncertainty with. And so there's three other pieces of information that we want to pull off the chart. First is if we wanted to get the enthalpy of this system, well, we'd follow this solid line up, and we would be able to read that the enthalpy in this case, this is going to equal 70. This would be a kilojoule per kilogram. And so that is the first thing that we'd be able to read. So we don't even have to worry about our calculations. We can just look that up. And remember, that is the air plus the water. So that is the enthalpy of the moist air that we have. In terms of other temperatures that we want to be able to read, we said we had three main temperatures. The second temperature after the dry bulb temperature was the dew point temperature. So the dew point temperature would be as if we took this, we cooled it down, and then we move completely vertical. Now, I didn't quite get that perfect, and so this would be the dry bulb, or today our dew point temperature. This would be about, let's say it's about 20.5 degrees Celsius. So there we have the dew point temperature. And then the last temperature we'd want is the wet bulb temperature. Now we said the constant wet bulb line is the same as enthalpy. So if we follow the enthalpy line up till we reach the saturation condition, and then we just move vertically, that gives us the wet bulb temperature. So again, this would be T wet bulb. This is T dew point, and this is T dry bulb. And so in this case, the wet bulb temperature be 21, 22, about 23 degrees Celsius. And so this is how we're going to be using the psychrometric chart. It is going to be good for all HVAC applications. And so again, the key thing that we want to be able to do is once we're able to establish this point, we're very quickly able to establish all of the other parameters by just drawing lines of constant basically constant horizontal, constant vertical lines, and then one constant diagonal for enthalpy and the wet bulb temperature. And so we'll pick up from this point on Thursday, where we'll start talking about HVAC applications and using this for solving essentially problems. So that is where we'll end today. I know I went a little bit long, but I wanted to try and get all of this in. Again, we'll spend a little bit of time reviewing this on Thursday. Otherwise, just a reminder, no lab this week. It will be online only, so if you do have questions while you're finishing up the CFR engine lab, feel free to ask during the lab period. I'll be available. But again, we are not meeting in person for lab this week. Okay, so that is it for today. If you have any questions, please let me know. Otherwise, have a good rest of the afternoon, and I will see you again on Thursday.